Hi everyone. For this week and the next several weeks, we're going to be talking about the mathematics of the ancient Greeks. So this mathematics is particularly important because it, more so than any of the other mathematics of the ancient world, has influenced the way that we do mathematics today. So how is this mathematical viewpoint of the Greeks different from that of other ancient civilizations? Well, if you look at the ancient Egyptians and Babylonians, for instance, the documents that we have from them that pertain to mathematics are entirely computational in the sense that, you might see a document with a problem and then a solution, and another specific problem and another specific solution, without any attempt to explain a general method or to convince the reader that any kind of method in the background might be true. Now, that's not to take anything away from the Egyptians and the Babylonians. They produced some brilliant work, but their point of view wasn't a conceptual point of view. Their point of view was not to convince someone else that a method was correct. It was just simply to perform a calculation. The Greeks, on the other hand, they were interested in the conceptual basis of mathematics and in logic and in proof. And in that sense, they are tied very closely to modern mathematicians. In fact, J.E. Littlewood, who was a very famous mathematician of the early 20th century, said of the Greeks that they are not just clever schoolboys, they are in fact fellows of another college, which was his way of saying that we would recognize Greek mathematicians as being our colleagues. They would fit well in the modern world. So we're going to look at Greek mathematics, and as you see from perhaps the top of the slide, the Greek mathematical era spanned 1,000 years. So there's no way that we can, touch upon any significant portion of Greek mathematics. However, there are a few areas that we will touch. And in fact, in this week's lesson, we're going to be talking about compass and straight edge constructions. So the Greeks were very fond of these constructions that you make with compass and straight edge. In fact, a compass, remember, is just a device that you use to make circles. A straight edge can be used to draw lines, and these two together can be used to make a variety of figures and to solve a lot of different types of problems. In fact, when we study Euclid's Elements here in a week or so, you'll see that the axioms of Euclid, most of them, the very most basic things in Euclid's Elements, have to do with acceptable ways that one can use a compass and straight edge. So anyway, before Euclid, there was a guy named Hippocrates who lived about maybe 500 BCE, and he was very interested in these geometric constructions. And one of the things that he managed to do was what we call square a lune. Now, what does that mean? Well, a lune is a crescent-shaped region. It's a curvilinear figure. And what Hippocrates was able to do was to take one of these things and use compass and straight edge and produce a square of equal area. So the important thing about doing that is that, we can find the area of a square fairly easily, and this translated to a way that one could find the area of one of these special lunes. So the important thing about this construction is that it led people to believe that it might be possible to square the circle. So there are three very famous construction problems of antiquity that were left unsolved really until the 1800s. One of those was whether it was possible to square a circle. So that is, I give you a circle, you pull out your compass and straight edge, and you attempt to produce for me a square of equal area. So for the longest time, for thousands of years, it was unknown whether it was possible to do this. And then finally, in the 1880s, a guy named Lindemann proved that the number pi is a transcendental number, And this fact was the fact that was needed to prove that it is indeed impossible to square the circle.